Hello everyone, this is Narges from University of Klagenfurt, and today I will present to you our accepted paper in the CCGrid 2021 conference with the title of a two-sided matching model for data stream processing in the cloud fog continuum. My co-authors are Dragi Kimovsky and Rodopordan from University of Klagenfurt. Firstly, I will give an introduction to our work, then I will present the state of the art, our CODA proposed model, the evaluations, and at the end I will conclude this talk. The world is witnessing an exponential growth in the amount of data generated in the presence of the internet connectivity. Latency sensitive and bandwidth intensive type of data stream processing services such as the social media applications or even the IoT-based applications are amongst the dominating traffic generators in today's world. Processing such data streams in nearly real time requires a vast amount of resources. The processing, storage, and the network resources to be in the proximity of the data sources. Therefore, the idea is that to filter and process such a data before sending them to be processed into the cloud data centers. By placing some micro data centers or femto data centers, which are directly connected to the base stations closer to the users or the source of the data. Also, there has been some routers which are giving this capability to the users to run some virtual machines on them and then be managed by the users themselves. Also, there is another idea to consider some clusters of single board computers consisting of the Raspberry Pi devices or GPU-enabled NVIDIA Jetson Nano devices, which can process a lower performant ML-based model to be trained on the user's data. Therefore, it had been the motivation for us to investigate how to manage the heterogeneous computing continuum to allocate its resources to the type of applications which have a strict latency requirement, and even based on the data that they are generating and need to be retrieved and processed, the bandwidth intensive type of applications. Investigating the state of the art, Murtazavi et al. In 2017 proposed cloud path by considering to do the processing and storing the data of the applications on a progression of the data center based on their computing and storage capabilities. Zamani et al. In 2017 proposed a semi-real-time data stream processing approach at the edge of the network. They have also considered the SDN aspects in order to manage the network devices. Gupta et al. In 2017 proposed a hierarchical placement strategy in the fog and cloud environment. They have also proposed a tool from which we have used in our evaluation. Sharqiband et al. In 2018 proposed a matching-based model in order to allocate the cloudlet to the IoT users by optimizing the response time and the cost for data processing. White et al. In 2018 proposed a greedy approach to identify the resources that minimize the service response time by specifically reducing the end-to-end event latency. Renat et al. In 2019 proposed an operator placement strategy aiming to minimize an aggregate cost, which covers the end-to-end latency, the data transfer rate, and then the messaging cost. Aral et al. In 2019 proposed an approach which has considered the trade-off between the resource utilization and then the proximity to the users of the application. Specifically, they have targeted the video streaming application, and they have compared their work with the content delivery network approaches and then the cloud approaches. Therefore, it had been our idea to propose our model, whose name is CODA, which addresses the problem of deploying data stream processing applications on heterogeneous devices. Our model utilized the matching theory principles, in which we consider the application microservices on one side of this matching, and then the other side is the resource which requires to lower its traffic. Firstly, we have modeled the application side. An application consists of different microservices which are interconnected to each other for flowing the data among each other. And we have considered that an upstream microservice will flow its data towards its downstream microservice. While we have considered two different microservices, such as microservice source and microservice sink, which are directly connected to the source and sinks of the data streams. From the other side, we have also modeled the resources, in which each resource is modeled based on its processing elements, storage elements, and also we have defined another parameter which is based on the utilization of the device, whether that device is capable of allocating and hosting multiple microservices or not. We have also considered the network channel between each two resources based on the latency that network channel has, and also the bandwidth that those resources can have while transferring the data between each other. In our model, firstly, we rank the resources for each microservice, as you can see. And then also we have ranked for each resource the microservices, such a preference list. Then we have used these rankings and these preference lists in order to match the microservices to the resources. So firstly, please let me to explain about the ranking methods. We have considered two different ranking methods. One of them is the microservice-based ranking, in which we have considered the microservice time. And then the other one is the resource side ranking, and for which we have considered the residual bandwidth by considering that one specific microservice will be hosted and allocated to one specific resource, and how much is the residual bandwidth after this allocation. For microservice side ranking, as I said, we have considered the microservice time. This microservice time is consisting of the element processing time, for which we have considered two different components. One of them is the computation time of processing each data element by one specific microservice, which has been allocated to, for example, resource RJ. The other component of the element processing time is the transmission time, and then the channel latency, by considering that there will be some transmissions and transferring of the data between each two subsequent microservices allocated to two different resources. Then we have considered the different number of elements, of course, a limited number of elements that one data stream has, and then we have calculated the total stream processing time, or as an abbreviation, we have used the microservice time for that specific microservice. On the other side, for the resource side ranking, we calculated the residual bandwidth by considering the difference between the available bandwidth between each two resources and the amount of data that are being generated and being transmitted between each two subsequent microservices hosted by different resources. Also, we have considered the ingress data rate by which the data will be transmitted and then on the destination microservice side will be processed. Then we have defined the resource allocation problem as a matching game between two finite disjoint set of players. One set is the microservice and then the other set is the resource. Let's see how the algorithm and then how the matching based on these rankings will work. As you can see previously, each microservice has ranked the resources, and also each resource has previously ranked the microservices. So as our algorithm is the microservice optimal based algorithm, we will start with the microservices. M1, microservice M1 will look into its preference list and we'll see that R1 is in its highest rank. Also, R1 will look into its preference list and sees that previously it has ranked M1 in its preference list. Therefore, they will be tentatively matched to each other. Then we will switch to the next microservice, which is M2. M2 will look into its ranking list or preference list and sees that R4 in its highest rank. Then R4 also will look into its preference list and sees that M2 is in its actually the highest rank. Then these two also will be tentatively matched. The next microservice, which is M3, will look into its preference list. R1 is in its highest rank. And also R1 will check its preference list and sees that M3 is in its preference list. And as R1 has enough capability to allocate a different number of microservices, so it will accept the matching to the M3. So they will be tentatively matched to each other. Afterward, M4 will look into its preference list. It has ranked R4 in the highest rank. R4 has also ranked, although lowest, in its preference list. So up to now, as R4 does not have any other choices except than M2, so it will tentatively being matched to M4. Then in the next step, M5 wants to be matched to R4, but it sees that R4 has been previously matched to M4 and M2. Therefore, R4 will look into its preference list and sees that M5 is in a higher rank than M4. Therefore, the matching to M4 will be removed, and instead of that, the matching to M5 will be accepted. In the next step, M4 and R4 both will remove each other's from their preference list. M4 will look into its preference list and sees that R1 is in the highest rank, but previously R1 has been matched to its highest rank microservices. Therefore, M4 and R1 will remove each other from their preference lists. Then for M4 just has been remained one resource, and that's resource number 3. Then they will be, then actually R3 will look into its preference list and sees that previously it has ranked M4, and also it has not been matched to its higher rank preference list choices. Therefore, these two will be tentatively matched to each other. At the end, as none of these two sides of the of the game will prefer the other preferred choice than the current matching. So we can say that this matching is stable. Let's see what we have done for our evaluation. For our evaluation, we have designed a use case based on the video stream type of application. And specifically, we have targeted the traffic sign classification for evaluating our work. As you can see, considering that some videos will be captured by some cameras that have been connected to a car or to a vehicle. So those cameras will capture some videos, and then these videos will be fed into our mentioned use case. This use case consists of different microservices such as the encoding, framing into, and for example, for dividing the application and the video into different frames, and then some machine learning based inference and training model. And at the end, the result will be packaged and will be returned to the user of this application. In this case, it's the driver of the car, for example. We let the driver to know that there is a traffic sign on the roadside, for example, by considering that the number is 200 kilometers per hour. So it will be an alarm for that specific driver. For experimental setups, we have to consider actually the simulation and also the test bed. Because it was a better idea to check the scalability of our method in terms of the simulation, and then at the end, if we were sure, we could switch to our considered and our provided test bed. For the simulation, we consider the iFoxing simulator, and then for the test bed, we consider the C3, which is the abbreviation of the Corinthian Computing Continuum test bed. It has different levels of the computing resources, the cloud resources, the fork resources. It resided in Klagenfurt and also Vienna, and also in our department, we have some sort of cloud-based, and then they are connected to a gateway machine by having a SDN OpenFlow router. They are interconnected to the single board computers. For further information, I ask you to visit the following website. For evaluating our work, we designed two different metrics. One of them is the stream processing time, which is related to the microservice sync. So we just consider the completion time of the last microservice of the application, considering that, for example, the structure of the application is as follows. Therefore, the completion time of the application will be calculated like this, based on the stream processing time. And also from the other side, we have calculated the total streaming traffic by considering the aggregation of the traffic that is being passed through the network channels between the resources. Then we compared our work with three state-of-the-art. One of them is the cloud-based, and the other two approaches are cloud and fog-based. One of them is RTRP, and the other one is the cloud path approach. For the simulation scenarios, we consider two different scenarios. In one of them, we modified the CPU load, and then we bounded the data size. And then in the second scenario, we changed and we modified the data size of the applications, and also we have bounded the CPU load. You can see the result in this slide, and our approach almost had up to 20% in terms of the stream processing time. in comparison to other approaches because it targeted the fog tier or fog layer 1 instead of fog layer 2 or the cloud resources. And also in terms of the traffic, we had some sort of improvement, although you can see that by changing the CPU requirement of the application, the traffic does not get changed. Although by changing the data element size, the traffic will get changed and almost it will get decreased because for a specific amount of data that will be produced in a specific CPU, simulation scenarios, this scenario will get finished earlier and then the network will get to its saturated state. For the real testbed scenarios, we have designed two different scenarios. In one of them, we changed the encoding bitrate, and then in the other one, we changed the frame size of the videos. In our evaluation, we reached up to 45% better stream processing time and up to 20% better streaming traffic. Although in comparison to the two other state-of-the-art approaches, we couldn't reach to that much improvement, although it was somehow 1.3%. But the reason is that because if we scale up the testbed scenarios, we can see that our approach can show itself better. But in this case, for example, for that specific video size that we considered, we couldn't reach to that much difference, for example, between the approaches. But CloudPath's approach, because it had targeted and also the progression of the data centers, we can see that it has some sort of differences with other approaches. Okay, in this talk, actually I proposed and presented our CODA model for running stream processing applications on the cloud fog resources. We have considered the stream processing time and streaming traffic as our main goal in this model. And at the end, we achieved up to 45% lower stream processing time and up to 20% lower streaming traffic. In the future, we plan to investigate the scheduling algorithm based on the matching theory principles, and we plan to inspect the dynamicity of the user's application and also the resources and the computing resources of the computing continuum. At the end, I would like to thank you for your attention, and I would like to attract your attention actually to our website to visit it, and also the CODA model is outsourced in the GitHub repository. Thank you.